Okay, Jai Hind to all. Today I am here to present one of the lectures on topic ladder structures under the subject digital signal processing KEC 503, which is running in 5th semester of AKTU syllabus. And I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC. And first of all, before starting this lecture, I'll explain that why ladder structures are actually required. So what happened, if we'll see the IIR filter realization, there are two types of realization, IR filter realization and FIR filter realization. So in case of IR filter realization, we are having the transfer function. In the transfer function, we are having the poles and zeros both. And we have seen the various realization structures, like in this case, we have seen in IIR realization, if you will see IIR realization structure, then we are having these structures like direct form structures, in which direct form 1 and 2 both are there. So in case of direct form realization, what happened, whatever the transfer function given to us, we will simply realize that transfer function. So there is no flexibility. In case of this direct form realization, there is no flexibility. We have to realize the transfer function in the manner in which it is given to us. So there is no flexibility in it. Then we have seen after it, in case of we'll differentiate, if we want to differentiate between direct form 1 and 2, then we can see that in direct form 1, we will first realize zeros and then poles, and in direct form 2, we realize first poles and then zeros. So direct form 2 realization is generally used because it is canonic in nature, means the number of delay elements in the structure is equal to the order of the transfer function. So generally we will implement direct form 2, or by default realization, if somebody will tell that it is the direct form realization. Then after it, we have gone through cascade realization. Okay, so in cascade realization, what happened, we will divide our transfer function in such a manner so that we can present that transfer function in form of 2 or more subsystems, and then we will realize each of the subsystem or the transfer function in direct form 2 realization. Okay, so the issue with this cascade realization, first of all, the advantage with this cascade realization is that when we will implement the structure, the overall transfer function is basically the multiplication of these two transfer functions, and we can directly find out the poles or zeros of the transfer function from the cascade realization structure. The issue is that if we will see the cascade realization, then in the cascade realization, we are having the structure of like this. We are having two systems, H1Z and H2Z, and we are simply applying input XZ here, and output we are getting YZ from here. So we will see here, when we will apply input, then that input is passed through the first subsystem, and then the output of the first subsystem will act as input to the second subsystem. So you can say this cascade realization structure is somewhat slow. Okay, so for resolving this issue, we have gone through parallel realization structures. So if you will see parallel realization structure, then in parallel realization structure, we are implementing our structure somewhat like this. Here you can say this is the first subsystem, and here it is the second subsystem. Okay, so the advantage of this type of structure is that the input that we are applying here is simultaneously applied to both the subsystems. So what happened when we will do this? So the speed of realization is fast in this case, because input is simultaneously applied to both the transfer function. But because of parallel realization, you can say complexity is high in this case. Okay, so but if you will see all these type of structure, there is one disadvantage of these type of structures, that these type of structures are sensitive to change in parameter variations. Means if the parameters are changed due to some change in the environment, then what happened, the overall transfer function value will become changed, and you can say the system will may become unstable due to the change in the parameter variation. So we require a structure wherein coefficient sensitivity should be low. So if coefficient sensitivity will be low, then in that case we can you can say we can easily make a structure which will not be affected by the environment. So in this category, the structure that we use is basically is the ladder structures. So that's why you can see here it is written that filters realized using ladder structures have desirable coefficient sensitivity properties, means small changes in the filter parameters have little effects on its performance. Means what happened, these type of structures are more robust. So what happened, first of all, these type of structures are less sensitive to change in the parameter variations, and because of they have because you can see that the small changes in the filter parameters have little effects on its performance. Okay. Now, if we'll see a ladder structure, so you can see the general transfer function of for an nth order ladder structure can be represented like this. So this is the transfer function. You can see both poles and zeros are there because we are realizing IIR structures. So you can see a n z to the power minus 1 plus a n minus 1 z to the power n plus 1 plus up to so n a naught upon b n z to the power minus 1 plus b n minus 1 z to the power minus n plus 1 up to so n b naught. So what are these a n minus 1, a1, a naught, or bn minus 1, b1, b naught? All these are filter coefficients. All these are filter coefficients. Now there is one thing in mathematics, that is continued fraction expansion. So if we want to represent this transfer function in ladder form, so first of all we have to do the continued fraction expansion of this transfer function. Okay. So once we can represent this transfer function in its continued fraction expansion form, then we can obtain the structure which is we can obtain the transfer function Hz which is of like this. Okay. So we can represent this type of transfer function in this form: alpha naught plus 1 whole upon beta 1 z to the power minus 1 plus 1 upon whole upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus up to so n 1 upon alpha n. Like this you can write this transfer function. So the important thing is that how we can obtain this type of structure, or how can we obtain this type of transfer function. So we can see here that important thing is that the order of the numerator and the denominator will be the same in this case. So we can obtain this type of thing by dividing numerator from the denominator itself. But that task will be, you can say, difficult. So for that there will be some procedure we will adopt, based on which we can make it like this. So I am just telling you for your understanding that how we are getting this alpha naught. Alpha naught is some coefficient which is the constant value. Why we are getting this constant value? Because we know this order is z to the power minus n in numerator and denominator both. So first of all, when we will divide it, so we will get some constant value. Okay. Then if you will again, then you will get the remainder, and then again you will, if you will again divide, you are getting this type of value. So by dividing the transfer function from denominator to numerator, you can say this type of thing is actually difficult. So we are solving it using a method given by Routh. So first of all, we will make a Routh array based on these coefficient values, and based on this transfer function we will make an Routh array. And after making Routh array, what we will do basically, we will make a complete Routh array, and from the first column of the Routh array we can calculate these coefficient values which are alpha naught, beta 1, alpha 1, beta 2 and alpha n. And maybe any value, if let us suppose n equals to 5, then in that case you are having the last coefficient value as alpha 5. Okay. So how we will make a Routh array, we will see first. So you can see here in this slide, we will write like this, because the highest power of highest order is n. So z to the power minus n corresponding to numerator, then z to the power minus n corresponding to denominator, and then second term that will be z to the power minus n plus 1, sorry it is minus n, and then for denominator, then for numerator, then for denominator, and up to so n. And our last value is z to the power 0. So z to the power 0 is 1. So that's why we are writing it 1 and 1 here. Okay. Now we will write the coefficients. Coefficients you can see the coefficients of numerator are an minus 1, an minus 2 and up to so n, a1, a naught. Last value is a naught. So, we will make a table like this, then we will write the coefficients of denominator like bn, bn minus 1, bn minus 2, b1 and last value is b naught. Now, what we have to do, our aim is to complete this first column of Routh array, because this first column of Routh array is responsible for calculating all these coefficient values alpha naught, beta 1, alpha 1, beta 2 and alpha n. So, all these coefficient values we can obtain only when we will get all these coefficients value. Okay. So, an and bn you are having this table. Initially, you are having this complete row, these two complete rows, and with the help of these two complete rows, we will obtain all these coefficients. Like if you will see Cn minus 1. So, how Cn minus 1 will be calculated? If you will see Cn minus 1 will be simply calculated as this coefficient will be simply calculated as Bn into A of n minus 1, then minus sign, means we are doing this analysis first and then in second step we are doing this and we are doing minus. So, Bn into an minus 1 minus an into b of n minus 1 upon bn. This is the value. We will divide it this value. Okay. So, Cn minus 1 we can obtain using this formula. Then what about Cn minus 2? If you will see Cn minus 2, then for Cn minus 2 what you will do? You will again take this term, multiply by this term minus this term into this term divided by again this term. Okay. So, if you will write Cn minus 2, then Cn minus 2 will become Bn into A of n minus 2 minus An into B n minus 2 upon Bn. Okay. So, we have obtained this coefficient. Similarly, another coefficients can be obtained like Cn minus 3 will be Bn into An minus 3 minus An into Bn minus 3 upon Bn. Okay. So, once we will obtain this Cn minus value. Now, how we will obtain Dn minus 1? We will see Dn minus 1 can be obtained. How we will obtain Dn minus 1? Dn minus 1 will be obtained as Cn minus 1 into Bn minus 1 minus Bn into Cn minus 2. Okay. So, Dn minus 1 will be calculated as Cn minus 1 into Bn minus 1 minus Bn into C of n minus 2 and divided by this time C of n minus 1. Okay. So, we will obtain the value of Dn minus 1. If we require, if our order is higher, then we have to calculate Dn minus 2, Dn minus 3, all these values we have to count it. Okay. So, Dn minus 1 we will calculate like this, then we will calculate En minus 2, Fn minus 2, G naught and H naught. We will calculate all these coefficient values by this Routh array. Okay. So, once we have obtained all these coefficient values, okay, means once we have all these values of Routh array like An, Bn, Cn minus 1, Dn minus 1, En minus 2, Fn minus 2, G naught and H naught, then how we will calculate these coefficient values alpha naught, beta 1, alpha 1, beta 2. Here I am taking the coefficient values as starting from alpha naught, then beta 1, alpha 1, beta 2. You can also take values like alpha naught, alpha 1, alpha 2, but just for distinguishing that wherever this beta term is there, you are having a term of z to the power minus 1, means you have to multiply by a delay element. That is why I am taking these coefficient values like this, so that you can make this structure easily. There will be no difficulty for making the structure if we are taking these values like this. Okay. Now, how we will calculate alpha naught, beta 1, alpha 1 and beta 2? You can see here alpha naught is equal to An upon Bn, means first coefficient value is simply calculated from here. You have already calculated all these values. So, alpha naught will become An upon Bn. Then alpha 1 will be equal to, then second coefficient is beta 1. Beta 1 is Bn upon Cn minus 1. Then alpha 1 is Cn minus 1 upon Dn minus 1, like this. So, you can see here beta 1 is Bn upon Cn minus 1, alpha 1 is Cn minus 1 upon Dn minus 1. Okay. And if you want to calculate beta 2, then beta 2 will be equal to Dn minus 1 upon dn minus 1 upon E of n minus 2. Then after it, if you want to calculate alpha 2, then alpha 2 is En minus 2 upon f of n minus 2. Okay. So like this, you can calculate all the coefficient values which are required for the realization purpose. Okay. So if you'll see there, you can say for ladder structure realization, there are two parts. First part is to obtain the continued fraction expansion of the given transfer function, which we have already done. Now what we will do for obtaining the continued fraction expansion of this transfer function, we will put the values of all the coefficients that we have already calculated. Means we will put alpha naught, beta 1, alpha 1, beta 2, alpha n here. So we will get the transfer function hz, which is, you can say, why we have done this continued fraction expansion, so that hz can be represented in this form. And once hz can be represented in this form, we can make the ladder structure by using this form of transfer function. Okay. So now we will see, after getting these coefficient values, now how the structure is obtained. We are seeing some mathematical formulas, or you can say some mathematical form of representation by which we can understand that how by getting these coefficients we can make the ladder structure, or what is the shape of the ladder structure. Okay. So this is, you can say, let us suppose our system is represented by yz equals to hz into xz. Okay, where hz is the transfer function, you can say, of this form. Okay, alpha naught plus 1 upon beta 1 z to the power minus 1 plus r1 z plus 1 upon r1 z times xz. Now what is this r1 z? So we are making it like this, that all the terms after beta 1 z to the power minus 1, like whole of this term, we are assuming it as r1 z. Okay. And that multiply by xz, where r1 z you can say is alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon alpha 2 plus up to so on 1 upon alpha n, like this. Okay, multiply by xz. Now if we will multiply it by alpha naught xz, so we are having two terms, alpha naught xz, and this term multiply by xz, and we are assuming that this term is h1z. Okay, means this whole term is h1z. Okay. So you can write it like h1z into xz. Now if you want to realize yz, so your yz will be equal to simply alpha naught xz plus h1z times xz. So this h1z, you can say it is a subsystem. Okay. So you can say, you can see here that there is a plus sign in between. So you can say this is, there are two systems. One subsystem is this, another subsystem is this. So we will make a combination of these two. So if plus sign is there, it means these two subsystems are connected in parallel. So that's why we are providing input alpha z from xz from here, and we are multiplying it by alpha naught, and in the another part h1z multiply by xz. So this is the realization structure. So you can see now we are having equation 1 realization structure, means this is the structure. Now what we will do? Now we will explore this h1z part. Okay, what are the components involved in this h1z part, and we will explore those parts and put it over here. Okay. So first step in realization of equation is A, if means this is the equation A, if we realize equation 1 in parallel form, where y1z is the output of the subsystem having h1z as system function. Okay. So now we will see this h1z. So h1z we have already taken as 1 upon beta 1 z to the power minus 1 plus 1 upon r1 z. So we are solving it. Now what we are assuming that here, because h1z is there, so let's say output is y1z and input is xz. Okay, h1z is y1z upon xz. You can also see it from here. You can see here output is y1z. We are assuming that this output is y1z, or you can also write it as y1z. Okay, so yz equals to alpha naught xz plus y1z. Okay. So now we will solve this equation. So we will get y1z multiplied by this term equals to xz, and from here y1z equals to okay. So we will solve this. So R1Z beta 1 Z to the power minus 1 term will be there, and R1Z will be multiplied by XZ here. So we are having the term Y1Z equals to R1Z XZ minus beta 1 Z to the power minus 1 YZ. And what again we are assuming that, let us suppose this whole term is, let's say, X1Z. So your X1Z is XZ minus beta 1 Z to the power minus 1 Y1Z. So you can say Y1Z equals to R1Z into X1Z, and this X1Z equals to XZ minus beta 1 Z to the power minus 1 Y1Z. Okay. So now we will realize X1Z. Okay. So you can see here the X1Z is the input, R1Z is the system function, and Y1Z is the output. And what you have to realize, you can say, if you want to realize this, so X1Z is XZ minus beta 1 Z to the power minus 1 Y1Z. So you know Y1Z is here, so this minus sign you require. So this means this is in form of feedback. So minus beta 1, so for beta 1 coefficient we are using a multiplier with negative sign and multiply by Z to the power minus 1 Y1Z. And this term is coming from here. So X1Z means X1Z, this is the X1Z. So X1Z is XZ minus beta 1 Z to the power minus 1 Y1Z. Okay. Now you can see this is the realization of this equation. Okay. Now we will, now you can see there here for this subsystem XZ is the input and Y1Z is the output. And you can see from here for this system XZ is the input and Y1Z is the output. It means in place of H1Z, what we can put? We can put this whole subsystem. Okay. So now what we will do in the next steps, we will combining the structures shown in figure 1 and figure 2. So this is your figure 2 and this is your figure 1. We can, if we will combine these two structures, so we will get this type of a structure. Now combining the structure shown in figure 1 and 2 to yield the structure shown in figure 3. So we can see this is the structure given in figure 3. Okay. So you can see this is the alpha naught, and in place of H1Z, where is the input is XZ and output is Y1Z. So here is the output is XZ into and input is XZ and output is Y1Z. So we will put this whole structure in place of that. So this we have obtained. Okay. So this is our figure 3. Now again we are having terms in form of R1Z, and R1Z you have already seen. We have taken R1Z value as alpha 1 plus something. So now we will realize this part, and we will see the next step in the realization of SZ to obtain a realization of R1Z that can be used in figure 3 if we write the expression for R1Z in equation A. Okay. So from this you can say R1Z is equal to Y1Z upon X1Z, and this is the same equation that we have written previously. So now if we will realize this, okay. So if we will realize this, so you can see Y1Z is the output and X1Z is the input, and similar type of structure we have already implemented. So this time we will write alpha 1 for R1Z, we will write alpha 1 like this. In place of alpha naught we will write alpha 1, in place of minus beta 1 we will write minus beta 2, and in place of R1Z we will write R2Z. Okay. So now you can say in place of R1Z, where the input is X1Z and Y1Z, we can make this structure. So again this structure comes over here with the term R2Z, and again we will write the expansion of R2Z in such a manner so that we can make this structure complete. So this process will be continued. Okay. So this process will be continued until we will obtain the final structure shown in figure 5. So this is the final ladder structure that you will obtain. Okay. So you can say, you can see here all the alpha coefficients are like in form of multipliers and in feed forward path, and all the beta coefficients with negative signs are in feedback path. And the important thing is that how we will make this structure, wherever this multipliers are moving, means wherever the direction of these multipliers is there, we will put the adder. So one adder will be put over here, another adder we will put over here, and another adder here, 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 here and here. Okay. So this is how we will obtain the complete ladder structure. Okay. So now depending upon the value of n in this equation, we are having the continued fraction expansion, and in continued fraction expansion we are having correspondingly you can see this Routh array, and accordingly we are having these coefficient values, and according to these coefficient values first we will obtain this and then we will make the structure like this. Okay. Even if you are not understanding very much clearly about the derivation, you can make the structure like this. Okay. So you can see here are the dotted lines, because we do not know, this is a generalized form, for any value of n you can make this structure. So why we are calling it ladder structure, now you can see these are the rungs of the ladders, that is why we are calling it as a ladder structure. Okay. So now we will see one example that how we will calculate the Routh array coefficients, and how we will make the Routh array from the given transfer function, and from that given transfer function how we will calculate Routh array, and from Routh array how we will calculate the coefficient values, and then with the help of those coefficient values how we will make this structure. Okay. So you can see from here, like this is the question given to us. Okay. So 2 plus 8z to the power minus 1 plus 6z to the power minus 2 upon 1 plus 8z to the power minus 1 plus 12z to the power minus 2. Now we will realize this using the ladder structure. Okay. So first what we will do, we will make Routh array, the highest value of n is 2, here n equals to 2. Okay, here n equals to 2. So you will make Routh array, starting value is z to the power minus 2 corresponding to numerator, then z to the power minus 2 corresponding to denominator, then z to the power minus 1 corresponding to numerator, and then z to the power minus 1 corresponding to denominator. Okay. And then these are the coefficients of z to the power 0, means 1 1. Okay. Now we will write the coefficients. So here is the term of z to the power minus 2. So this 6 value is here, then 8, then 2, and in denominator 12, 8 and 1. Now how we will calculate this value? So as we have already discussed, this value can be calculated like let us say this value is a. So a equals to 12 into 8 minus 6 into 8 upon 12. So this value will be 4. So we are getting this value 4. Okay. Next value 3 by 2, how we have obtained? We have, let us say this value is b. So b is 12 into 2 minus 6 into 1 upon 12. So this value will become 3 by 2. Okay. 18 by 12 means 3 by 2. So we are having this value 3 by 2. Now there is no coefficient here, so all these coefficients are become 0. We are not writing these values here. Okay. Because there is no term here, so after that there will be no term here. Okay. Now we have to calculate this value. So how we will calculate this value? Let us say this value is c. So c will be equal to 4 into 8 minus 12 into 3 by 2. 4 into 8 minus 12 into 3 by 2 upon 4. If you calculate, you will find that this value is 7 by 2. So we will get this value. Okay. Now how we will get this value? How we will get this value? This value is 4 into 1 minus 12 into 0. How? Let us suppose this value is d. So d is 4 into 1 minus 12. Here is 0. So minus 12 into 0 upon 7 by 2. Okay. So this value will become 5 by 4 into 1, 7 by 2. Okay. So you will calculate, this value will become 5 by 14. Okay. You will multiply 7 by 12 into 0 minus 4 into divisor, so this will become 5 by 14. Okay. Similarly, when you will calculate this value, last value will become, let us say E is 5 by 14 into 1 minus 7 by 2 into 0 upon 5 by 14. So by default this value will become 1. Now once we have obtained all these values, okay, now once we have obtained all these values, you can calculate the values of coefficients. Now how many coefficients will be there? First of all, alpha naught will be there. So alpha naught will become 6 upon 12. So alpha naught will become 6 upon 12, that will be equal to 1 by 2. Then alpha 1 equals to, sorry, next coefficient will be beta 1. So beta 1 will become 12 by 4, that is 3. Then alpha 1 is you can see here 4 upon 7 by 2. So the value is 8 by 7. Then after it beta 2 will be 7 by 2 upon 5 by 14. Okay. So this if you solve, you will get 49 upon 5. And last value alpha 2 will become 5 upon 14 divided by 1. So this value will become 5 upon 14. Okay, is it okay? So we have calculated all the coefficient values. So after calculating all the coefficient values, you can see that you will stop at alpha 2. You will stop at alpha 2. Okay. So now you will write the continued fraction expansion of this transfer function hz. So alpha naught plus 1 upon alpha naught plus 1 upon beta 1 z to the power minus 1 plus sign is missing, 1 upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon alpha 2. So 1 upon alpha 2, 5 by 14, or you can write it also like 14 by 5. Now it is what is the reason behind that you are doing the continued fraction expansion? Because it is very difficult to write directly from here to here. But if you will solve this transfer function now, you will get this value. Okay, means if you will check that whether you are getting the correct continued fraction expansion of this is not. So you will check, you will solve this. You can easily solve it. First of all, you will take the partial fraction here. First of all, you will take the LCM here, and then step by step you will moving in this direction, and finally you will obtain this transfer function hz. Okay. So this is the way we will do the continued fraction expansion for the given transfer function. Now next step is we have to realize it. Okay. So for the realization of this continued fraction expansion coefficients or the ladder structure, we have already seen that the structure is like that. So xz and yz is here. First of all, alpha naught comes over here, which is equal to 1 by 2. Okay. And then beta 1. Now you can see here in this structure, the coefficient is minus beta 1, and beta 1 you have calculated is 3. So that is minus 3 z to the power minus 1. And important thing is that signal flow is always towards the adder, like this signal comes over here and this signal comes over here. The next step, you will write alpha 1 is 8 by 7. So this is 8 by 7. Now because adder is here, and how signals are traveling? Signals are traveling from top to bottom and from bottom to top in this direction. So you can say, okay. Now next is beta 1, then beta 2, this value is minus beta 2. So that will become minus 49 upon 5, and this value is 5 by 40. Okay. Now there is no adder required. The output that we are obtaining here is directly connected to here. Okay, isn't it? So so this is your alpha 2. So this is by which you can obtain the ladder structure realization for the given system function. And let us suppose if the system function is somewhat you can say more complex. Let us suppose if a term of z to the power minus 3 is also there, but important thing is that if a term of z to the power minus 3 is here, then it will also be here. It will also be here. So what happened? There will be some more exercise introduced, because you are having z to the power minus 3, z to the power minus 3 terms will be there. And then you will, if you will see it, then alpha 2, after alpha 2, here you have it stopped at alpha 2, but for that case when n equals to 3, you will reach up to alpha 2 after alpha 2 you have to calculate beta 3 and alpha 3 also. And this structure you can see there are 2 more ladder rungs will be added in the bottom, and you will put adder here and you will make this complete structure. Okay. So, this is the process by which we can make the ladder structures. So, these structures are you can say very important type of structure in case of IR filter realization, because of we have already previously discussed due to the coefficient sensitivity property of these coefficients. Okay. So, this is the way for n equals to 3 you have calculated, for n equals to 4. But the important thing is that in this whole case is that all the coefficients of this first column of Routh array, and should be there will be no 0 here. If there will be any 0 here, then these coefficient values will become infinity, and we will not be able to solve this ladder structure. So, in that case we have to go through the Routh different type of properties of Routh array, then how can we eliminate those type of difficulties in this case. But that is not required here. So, so this is the way these ladder structures are represented. So, thank you very much and for listening this particular lecture. If there are any queries you can ask me, and thank you so much.